Good afternoon, everyone. My name is Dejan Gvozdic. I am professor of physical and quantum electronics and optical communications. At the time being, I serve as the Dean of the School of Electrical Engineering at the University of Belgrade, Serbia. First of all, I would like to express my gratitude to Professor Kramp for the invitation and to thank organizers for the opportunity to give a talk at this prestigious conference and symposia. Of course, I must also express my regrets and disappointment that I'm not with you today and with the fact that I could not obtain visa on time. Let me turn to the topic of my talk. Although there are several schools and institutes related with photonics research, the topic of optical frequency comb is covered by 3 institutions in the Western Balkans. At the Faculty of Electrical Engineering of University of Ljubljana, Professor Boštjan Batagelj used to study stabilization of optical frequency combs by self-injection over the optical fiber. In Croatia, there is a quantum technology group at the Institute of Physics of the University of Zagreb, which exploits optical frequency combs for cooling and spectroscopy. Here in Serbia, optical frequency combs are studied by my group at the School of Electrical Engineering in Belgrade. In the rest of the presentation, I will give a short review of our research in the field of optical frequency combs. Our first project on optical frequency combs was completed in cooperation with Dublin City University and Professor Liam Berry. The idea was to provide simple, robust and power-efficient scheme for generating significant number of flat frequency combs. The common approach is to use cascade of Mach-Zehnder modulators with the continuous wave optical source. These configurations demand high amplitudes of RF generators, which can go up to 6 to 7 VPIs. However, we propose scheme based on cascade of gain-switched laser and Mach-Zehnder modulator, which can be driven with the fraction of VPI. The gain-switched laser cannot provide so many flat lines. Usually it gives 3 lines if it's driven with the harmonic signal. In case when it's used in cascade with the Mach-Zehnder modulator, the role of modulator is to produce replica of these laser combs shifted to adjacent frequency range. In order to investigate feasibility of this idea, we made a numerical model of both stages. The model of gain-switched laser stage is based on multi-quantum DFB rate equation model, which accounts for carrier density in the barrier states, carrier density in the photon density and phase. The model is more realistic than standard model and can help in comparison with experimental results. The stage with the Mach-Zehnder modulator exploits dual drive Mach-Zehnder modulator, which transfer function model is presented by this Jacobi-Unger expansion. In this model, we define 2 important parameters, eta and psi, related with the bias voltage and amplitude of RF signal, respectively. Cosine of eta represents the weight coefficient for even harmonics. Sine of eta represents a weight coefficient for odd harmonics. Here, as shown in the figure, are presented various spectra. Gain-switch laser provides 3 flat lines, and this is the result of gain-switch stage, which frequency range is 2 times larger than the frequency of RF generator in gain-switching stage. However, contribution of the lines minus and plus 2 is significant and should not be neglected. Therefore, instead of to shift spectrum with only 3 lines, we decided to shift 5 lines from -2 to +2. This shift demands 4 times higher frequency than the frequency of gain-switch stage. In order to provide it, we turn down odd harmonics of dual drive modulator by setting up sinus of eta to 0 and this corresponds to DC voltage equal to V pi. Since only even harmonics contribute to the shift of laser spectrum, the frequency of generator in Mach-Zehnder stage should be just twice the frequency of generator in the laser stage. In this case, should be 19 GHz. In order to overlap original and replica spectra with the same magnitude, it is necessary to equalize constant part of Mach-Zehnder transfer function dependent on Bessel function of first kind, J0 of psi, and second harmonic dependent on function J2 of psi. This result is achieved for surprisingly small voltage, a little bit more than half of V pi. Due to positive and negative frequency shift, 3 lines are multiplied by 3, which essentially leads to 9 comb lines that you can see here in the spectrum. However, the overlap of line +2 with the replica of line -2 due to positive shift, and similarly overlap of line -2 with replica of line +2 due to negative shift, provide 2 additional lines with almost same intensity as other 9 lines. And therefore, at the end, we end up with at least 11 flat lines. Let's see the experimental results. Here you can see the laser spectrum. 3 flat lines can be clearly seen. The asymmetry of the spectrum is a result of finite Lyman enhancement factor. The next figure shows standalone spectrum of Mach-Zehnder modulator in case when odd harmonics are suppressed, as you can see here in the figure, by setting DC voltage to V pi, while fundamental and second harmonic are equalized by setting amplitude of RF signal to half of V pi. So you can see that these harmonics are more or less equal. And here is the final spectrum corresponding to cascade of gain switch laser and dual dry Mach-Zehnder modulator. The number of flat lines within the margin of 3 dB is 12. Here you can see excellent agreement with our theoretical prediction. This red envelope corresponds to experimental results, while blue dots correspond to numerical simulation, and 3 comb lines can be seen with 2 dB flatness. Match is also excellent for the whole cascade. There are 12 blue dots you can see here in the figure, corresponding to 12 comb lines with 3 dB flatness. The number of lines derived from experiment and simulation is the same. However, the number is by chance larger than 11, which is the number predicted by our qualitative consideration. Finally, here is our best simulation result predicting 20 comb lines with 3.8 dB flatness. This can be achieved by setting the amplitude of the RF signal to 3.14 V pi, which means pi times V pi, which helps to equalize the fundamental, the second, and the fourth harmonic, providing 4 additional replicas of the gain switch spectrum. The second project is completed in cooperation with the group of Professor Darko Zibar from DTU, which expertise lays in the machine learning in photonic systems. The goal of the project was to investigate possibility to reduce complexity of the scheme and to exploit solitary gain switch laser, which should provide a large number of flat comb lines. This is a typical inverse and complex optimization engineering problem where the goal is to find the driving signal characteristics that lead to the target frequency comb performance in terms of carrier to noise ratio, number of lines, and flatness. And for that reason, the current of the driving signal is represented by sum of multiple harmonics, which provides more flexibility in terms of current tailoring. The bias current amplitude of RF harmonic amplitudes and the relative phases are optimized using two gradient-free algorithms, particle swarm optimization, PCO, and differential evolution, DE. The numerical results lead to 9 comb lines of gain switch laser with 2.9 dB flatness. The current profile consists on only 3 harmonics, is presented in the figure, and you can see what is the profile of the current which is necessary to achieve these nine lines. A proof of concept experimental demo setup for frequency comb flatness optimization is shown in the figure. The multi-harmonic laser driving signal is achieved using the signal generators with synchronized clocks with frequency 5, 10, and 15 gigahertz respectively. An online experimental optimization using the differential evolution algorithm results in 7 comb lines with 2 dB flatness. And our third project is related with the development of a simple scheme for efficient generation of dual frequency combs based on gain switching. Most of the previous proposed schemes demand more than one device. We use a single gain switch laser diode driven by superposition of 2 electrical current forms based on sync and sync squared shaped current pulses. The modulation frequency F1 and F2 are set to F1 to 100 MHz and F2 to 100.25 MHz. Figure shows dual frequency comb for sync-shaped modulation current, represented by blue lines, and corresponding comb envelope, this is pink line, for given parameters showing the pink color. The frequency separation between pairs is constant, and it's approximately 200 MHz, while the separation of T of a single pair increases with increase of frequency separation from the central comb line. So as you can see here in the inset, these lines are close to each other, but the separation between dual comb T is quite small. But if you look at this inset, you can see that T of comb lines can be easily distinguished. So we define the comb span as a frequency region comprising T pairs which optical power lay in the range of 20 dB below the maximal power, excluding the power of the central node. So this is the range of power which corresponds to the frequency span of the comb. For this definition, the span for shallow modulation depth provides 48 GHz span with 240 T pairs, while for larger modulation depth we achieve 55 GHz span and 275 T pairs. For both current forms, higher line width enhancement factor alpha increases the power per T pair on the expense of spectrum envelope smoothness distortion. Sync pulses may provide relatively flat comb lines, but their spectral power efficiency is rather low, and it goes up to 6%. For sync squared pulses, simulation of the spectrum power efficiency goes up to 52% at price of lower flatness. In conclusion, I should mention that experimental verification of proposed concept is completed at Dublin City University by a group of Professor Liam Berry. We also plan to continue optimization of predistortion of the laser driving signal with some additional components which might help to improve the number of lines, their flatness, and carrier to noise ratio. In addition to all mentioned contributors, I would like to thank IEEE Photonics Society for financial support. Thank you.